Word problems here. The two big things word problem-wise or application-wise in this section are the extreme value problems that you've worked on. You've hopefully done the 8 that are in this section already and have started to try some of the ones that are in the textbook. Again, we're going to leave this 4.5 for now. We'll do that afterwards. The other type of applied problem we're working with here is called related rates problems. Before we do anything with that, let's talk about what a rate of change is. Yeah, I mean, you first learn about it. Well, you don't first learn about it when you learn about slope, but you talk about the slope of a graph. If you have a distance-time graph and you talk about how, what's the rate? The rate is called velocity or speed. But if you have distance in meters and this in seconds, what are the units on that rate of change? Meters per second. Okay, that's pretty obvious, right? Any two quantities you're comparing, you can work with rates of change. And at this point, we know that if we have some function that looks like this, we can still find the derivative. It's still going to be a rate of change. The derivative is the rate of change. Okay, derivative is the rate of change. It's the slope, it's the rate of change, right? The derivative is the rate that something's changing in. If you have a function, if you find the derivative of something, that's the rate of change. This thing that talks about related rates here is going to be something that's, I think, pretty useful, especially if you're taking physics or any other of the science courses, well, or this for that matter. Any formula that you know, such as that one, right, for area of a circle, if you want to know how the rates that those things are changing at, so I'll show you a visual here to give you the idea. So this is a circle. Now the concentric circles as you go out are just for kind of for your own reference to see. But if we take this and we start in the middle here and we make it larger and larger at a certain rate, so time's passing at whatever rate it's passing. There's two rates of change I could look at. I could look at the rate of change of how fast the radius is getting bigger. I don't know what units, like on the screen, obviously it's bigger than on my screen here, but if you measured it in, what units might you measure the rate of change of the radius? How fast is it changing per second? What do you think? You want to see it again? As amazing as it was. So the radius is obviously that line between those two blue points there. So if I try to do this at a constant rate here, how fast is the radius changing, you think? Just give me a estimate of some sort. 1 unit every 2 seconds, and maybe those units are, I don't know, whatever they are. I mean, the screen's much big up there, but it's about a centimeter on my screen here. So maybe a centimeter per 2 seconds, so half a centimeter per second. That rate is, obviously if I do it differently now, if I go like this and then slow and then faster or whatever, it can change, right? It doesn't have to be constant. But whatever that is, there's another rate we could look at, which is how fast the area is changing compared to time. How fast is the area changing compared to time? It's harder to think about area, right? It's easier to think about the rate that the length is changing and the radius, but the rate that the area is changing, how fast do you think this area is changing? How much are you gaining here? You can look at the numbers there, right? So when you go from, say, there, about 3, right, 3 units, to there, we gained about how much? 9, about 9 units in, and you said maybe it took me 2 seconds to go from there to there. So you gained 9 square units in 2 seconds. So what do you think the average rate of change from there to there was? What do you think it was? 4.5 from there to there. Is that going to be the same as when I do this one from here to here? No, it's going to be a lot more, right? You gain more pizza going from a medium to a large than from a small to a medium, right? Because pizza sizes seem to go like that, where they just add on a certain distance and it's always the same. So if you go a small pizza, obviously is not 2 inches in diameter radius, but if you go from there to there, you're gaining this ring. But intuitively, I think you know that if you go from there to there, this ring's a lot bigger. There's more area there, right? How much did I gain from the 1 to the 2? I gained 9, right? From the 2 to the 3, I gained how much? It was about 12. And this is about 28 or something. So you gain more that time, right? And you're going to gain more every single time. The rate of change here is not if you look at those two rates of change, are they directly proportional all the time? Like, how can I get from this one to this one? How is this rate related to this? Because they are related, aren't they? The rate that the radius is changing, if I go really slow, the radius is changing really slow. The area is also changing really slow, right? If I change the radius really fast, how does that affect how fast the area is changing? Faster, right? I mean, obviously they're related to each other. If you change the radius fast, area changes fast. If you change the radius slow, area changes slow. You can write a formula really easily for how those two rates are related to each other. That's what you're looking at. It's called related rates. Okay? So you're going to be able to write formulas for how rates are related to each other. So first of all, realize that the two rates we were talking about are dA dt and dr dt. dA dt is the rate that the area is changing with respect to time. Can I just say area to time instead of rate of change of area with respect to? We'll just say area to time, right? It might be in, what units might we have done there? Centimeters per, what would the area be? Not centimeters, what would the area be? Centimeters, square centimeters per second. And then radius, what units were we maybe using for that? Centimeters per second. So that's radius to time, right? Rate of change of radius to time. So those two rates are related to each other. You can write a formula if you know the way the quantities are related. This relates to quantities. It doesn't talk about the rates. This is just the quantities. This says that at any time, if you go back to that picture, like if you set the radius to be 3 here, or 2, or whatever, no, 3, let's do 3. You can figure out the area from the radius, right? How do you do that again? It says it on the other page, right? You take the radius and you do what? If you want the area, if you want how much is shaded in green, you take the radius, you square it, and then you times it by pi, right? So that's what that formula is saying. That says you take r, you square it, you times it by pi, and you get the area. If that's how the quantities are related, we can find out how the rates are related to each other by differentiating both sides of this with respect to time. If those are the quantities, what we can do is say, I'm going to write it again here before I differentiate it and leave some space in here. So I'm going to now say, if these are equal, then their derivatives with respect to time must be equal. If you do the derivative of both sides of that formula compared to time, as though time is the variable, the independent variable, then you'll get a formula that involves those rates, right? If I do the derivative of both of those, because this side, what is that side? How do I write that? The derivative of A I just write as dA dt, right? That's what we're looking for. That's one of the things we're looking for. So it's saying that rate has to be, what about the other side here? We're going to need the chain rule. What's it going to be? You want to take a shot at it? What's on the right side? The derivative of pi r squared? Yeah, the pi I'm going to put out here because pi is a constant, right? So you can put that outside. I'm going to write this down, the derivative of r squared. Now, if the bottom thing here was dr, what would the derivative of r squared be? It would just be 2r. But it's not an r, it's a t down here. So what do we have to do? We got to tack on one extra thing here. So, well, you need how, remember the chain rule is, how is r squared compared to r, and then how is r compared to t, right? This is 2r, but this is dr dt, or r prime, if you want. I would say it's better to use the d dt notation, or d dx notation for this, than the, like you would have probably written it like this, r prime, right? Except you wouldn't have scribbled the prime. Okay? You would have written that when you use the chain rule. You would have said it's 2r times r prime, because r related to t. But we're going to say dr dt. and that's what dA dt is. Okay, that's just the chain rule. So you got two parts there. You took the constant out. If you want the derivative of r squared compared to t, you first have to do r squared compared to r. That's what that is. And then r compared to t, right? If you wanted to put something else in there, you could say that this is pi times dr squared dr dt if you really want to, right? Because then you can see where both of those things come from. This one, I'm getting my colors confused here. Let's fix that. Because this dr squared dr is that 2r, and then you need r to t. Does that make any kind of sense to you? Your formula that you end up with is this. If you want to put this in order here, what would be the order that mathematicians would put those three things in? Pi times 2 times r times dr dt. What do you think? 2 pi r, exactly. You guys are on your way to becoming mathematicians. If you understand that random, it's not random. They somehow think numbers that are like, whole numbers, or not things like pi, that comes next, and then variables. And in this case, r is a variable, right? The radius can change. It's not a constant. This formula tells you how the two rates are related. This is saying to get the rate of change of area is equal to take the rate of change of radius, if you know how fast the radius is changing, and times it by 2 pi r. Does that make sense? Let's pretend for a second that this formula was a lot simpler here, that we didn't have this 2 pi in there. Let's pretend it just said the rate of change of area was twice the rate of change of radius. So that's not it, but just pretend it said that. What would that tell you? If this were, it's not going to work because the units are different. But if this were one rate and it was something centimeters per second, and times by 2, if this was like 7 centimeters per second, what would it say this rate should be? 14 centimeters per second. Now that's not even going to be the right units, because we know this was supposed to be centimeters squared per second. What was the thing that I erased there? Let's put it back in. 2 pi r. If you have something like, if we change the radius at 7 centimeters per second, and then we want to know how fast is the area going to change. If we change the radius at 7 centimeters per second, we also need to know where are you starting, right? So what this is saying here is, let's say I was at this point right here, at 4. Let's say I was at the radius was 4, and now I start, and at that moment I'm changing I'm increasing this at half a centimeter per second. So if I'm increasing this at half a centimeter per second, and we want to know how fast is the area changing the instant I hit 4 here. Okay, as I hit 4, how fast is the area changing at that given moment? Because it's different the whole way out here. We just said that the rate that the area changes is different from there to there as it is from there to there, right? It's different everywhere. Like it's not a constant rate, the rate that the area is changing. Even if I set the radius to change at a constant rate, the area is not changing at a constant rate. It's dependent on two things. It's dependent on the rate that I change the radius and on what the radius is at the moment. Okay? It's dependent on two things. This is dependent on the radius and the rate that I change the radius. Two things. So you need to know both of those if you were going to work out what the rate of change of area was. If I want the rate of change of area, I'd have to say, let's say it was the moment the radius was 4 centimeters, and I'm changing the radius at 7 centimeters per second. What's the rate of change of area going to be? I need a 2 and I need a pi in there. Let's get the calculator out and check that. So if I multiply all those things, if I say 2 times pi times 4 centimeters times 7, 175. So So roughly 176 or 175.9. 175.9 centimeter. What are the units going to be? Because you guys are good. You've probably taken physics and chemistry and stuff where you do unit analysis. Now, let's say you didn't know that the answer was supposed to be centimeters squared per second. How can you figure that out? Just by looking at the numbers you're multiplying.
Well, 7 centimeters.
You got centimeters times centimeters divided by seconds, right? So you got centimeters squared per second. The units should work out. The units that you're doing should work out. These units should over here be now centimeters squared per second. Okay, sorry, whatever. I've already got it over here. Those units should work out. So I don't need to write it over there. I have it over here. Okay, those units. That's telling you that you're gaining at the instant that I pass by here. If I'm increasing this thing at 7 centimeters per second, the instant that I hit 4, the instant the radius is 4, at that instant you're gaining 175.9 centimeters every second. That's the speed. If there was it's not a speedometer, it'd be like an areaometer. That's how fast you'd be gaining area at that instant. That's not going to be the same as if you were at the instant you hit 5, right? If I was increasing this at 7 centimeters per second, the instant I hit 5, I'm going to be gaining area at a higher rate than that, right? Because we would have put a 5 in here instead of a 4. That would be a higher number. And again, intuitively, if you think about this, the farther away from the center I am, if everything else is constant, the faster I'm gaining area, right? If I set this thing to go at a constant rate, the farther out I am, the more area I'm gaining at any given instant. Okay? You could work out the average change in area from one point to another point, but we're talking about the instantaneous rate of change and how they're related. This formula relates how the two rates are related to each other. Does that make sense? Can we do this one? Because it's a similar formula. Area is side squared. Or not to make it not to make the video have a higher rating here, but you know how we put x into the calculator as x times x times x. So if you said a equals s times s, I think my grade 8s would not like that formula, but we'll leave that one off. Never thought of it. Get it? Yeah. Thanks for saying that out loud there. Trying to make a subtle joke, and anyways, what do we come up with here? So again, if we try to think about what this is if you have a square here. Now this is not going to let me change it. It's going to click to the. Oh no, there we go. So if I'm changing it'll click back to the grid thing. If you're making this bigger at a certain, I need my other key here. Let's try that again. Need this key. So if we're doing this. We're making this now. I'm trying to keep it a square, but pretend it had to stay a square. Depending on how fast I change the side length, how fast is the area changing? It's obviously related, right? They're not totally unrelated. They're related to each other. The faster you change the side length, how does the area change? Yeah, faster, obviously, right? But is it proportional? Like if I double the rate that I'm changing the side length, does that double the rate that the area is changing? It doesn't, right? The area changes faster than the rate of change of area changes faster, but you can figure it out and then we can analyze it here. If I take this formula, if I take the derivative of both sides, so now I do d dt of s squared, what's going to be on the right side here? Well, what's the derivative of s squared if s was the variable? 2s. But since t is a variable, what do I have to multiply by? ds dt, right? To use a chain rule. So there's a formula that relates those two rates. It says if you want the rate of change of area of the square, it's related to two things. It's related to how fast you're changing the side length, ds dt, and it's related to whatever the side length is at this point, right? If you want to know how much area you're gaining at any given moment, it's related to both of those things. If you think about the square here, let's pause that for a second. If I go from that to that, how much area do I gain? I gain 5 squares, right? If I do that same thing here, if I add one more here, I gain 7 squares. The bigger the radius is, the more area you're gaining. So the rate of change of area is going to be related to how big the square is at any given moment, right? If you start with a big square and you add on a unit, you gain a lot more area than if you start with a small square and add on a unit. There I only gained 5 squares. Up here I gained a whole bunch, right? So the rate of change of area is related to the actual length of the side, but it's also related to how fast I increase it. At any given moment, if I'm increasing this really slowly, I'm not gaining area very fast. But if I change this fast, I'm gaining area pretty fast. The rate of change of area depends on two things: the actual radius and the rate of change, side length. The side length and the rate that I change the side length. So that's what that formula is going to tell us here, or what it does tell us, right? That formula tells us that it's related to two things here. Rate of change of area is related to rate of change of side length and the actual side length at any given moment. All right? You can take any formula that you know, or make up a formula in a situation if you want to know the rates of change of any given quantities in there. Right? This one's not any harder. It's got that fraction involved, but it's not a big deal. And there's lots of other formulas here. These problems just ask you to use those formulas. If you want this one says, what's the relationship between the change of volume and the change of radius if you have a balloon? You got to make some assumptions here. Let's assume the balloon is a sphere, even though it might not be exactly a sphere. And it says here, what is the rate of increase of volume? How fast is the volume changing? When the radius is 3 and the radius is increasing at a rate of that. You got to have two quantities given here for this. You got to know the rate of change of radius and the radius itself. Either take a pre-made formula for your volume of a balloon, right? Whatever it was, 4/3 pi r cubed. Generate the formula for the rate of change. So you'll have rate of change of volume is some stuff times rate of change of what's going to be on the other side. What's the rate going to be over here? dr dt. They're obviously related, right? Again, you change the radius of the balloon fast, the volume changes fast. There's some other stuff in there. Then you can sub in the quantities, right? Start with a formula, generate your rates formula, and then use your rates formula, right? If you like sort of steps, or here's how to do it, or whatever, we can write those things down up here. I'm going to write them right here. And my handwriting is such beautiful stuff, but I'm tired of looking at it. So let's use the actual capacity of the computer. I hate the here's how to do it. This. Just show me how to do this if you like that kind of thing. So let's actually get rid of that. That's goofy. Start with a formula involving the quantities. Generate a formula involving the rates. Does that make sense? So you got to start with something involving just the quantities and generate something involving the rates. Right? So starting the first, start with the quantities. Area is pi r squared, and generating the formula involves the rate of change of each of those. And then use the formula you generated. Okay, use known values to find unknown value. It's like any other formula. If you have a formula that has 3 variables and you know 2 of them, you can find the third one, right? Or whatever. If you know any of the values involved, as long as you know all of them except for one. So like that one that we had that was dA dt, and it was 2 pi r times dr dt. That formula has 3 variables. What are the 3 variables? You have to expand your understanding of the word variable past the grade 8 definition. What would grade 8 say? If I say what's a variable, what would they say? They'd say a letter. It's a letter, right? They wouldn't recognize that that's a variable. You can use more than one symbol for a variable, right? That's one variable, the rate of change of radius. This is another variable, and this is a variable. There's 3 variables involved in that formula. If you know any 2 of them, you can solve for the third. That's a concept you already know, right? It's just a formula like any other, except that those kind of things are variables, and so it makes it look a little more complex, but it's not. Okay. This formula, incidentally, with this thing here, dA dt is dr dt times 2 pi r. What does that actually represent? Just out of coincidence here, and you're going to find this as you work through some of the formulas. You'll find often the rate of change of area is, sorry, it's not a square. What am I doing? You'll find that the rate of change of the area of a circle, the area inside a circle, is related through the circumference of the circle. 2 pi r is the circumference. Right? So it says the rate of change of area is how fast the radius is changing times the circumference of the circle. That kind of makes sense, because where are you gaining the area as you make the circle bigger? Where is the area being gained? The outside, right? If this was a city, you could have an application problem where this was a city that's sort of circular and growing on the outskirts of the city. The growth is happening at the edge of the city, right? Not in the center. So as this is being gained here, you're gaining area around the outside, right? You're gaining area on the outside. So it depends on 2 things. It depends on how fast you let the radius grow, and it depends on how big the circumference is at any given moment, right? If this was growth of a city, if that's the circumference, you can gain area anywhere around there. If the circle is smaller, you can only gain area in a smaller distance there, right? So circumference times that. When you generate some of these formulas, look at what's left over here. Sometimes for the volume of something, it's going to involve the surface area times some other rate. There's lots of problems in here. I don't want to do this. In the past, I've done this where we've gone through a lot of these together, and I don't know if we've gained anything. You have the concept. There's going to be, I'll tell you that story at some point after you've tried the question, but, down here somewhere, we're going to start to talk about where you have 2 variables, right? You have 2 different things it depends on. So you're going to have formulas that have more than 2 rates in them. Not any different. You just might need the product rule or something like that, right? At this point, you must consider using the product rule, quotient rule. Like, make sure you read these things, right? Sometimes more than 2 quantities. I highlighted all the important words in that couple sentences for you. They're all important. Well, it's basically more than 2 quantities are changing. Can you get going on at least sort of the first section here, some of the problems? Again, you have the answers at the back. You can check, right? That's the idea.